Dan here at Rosia Maple Syrup. One of the most frequently asked questions I get about reverse osmosis systems is in regard to recirculation. So I wanted to post a quick video that provides a very simple explanation of what's going on and how it works. The type of recirculation I'm talking about specifically is a low pressure recirculation. So an outer loop, if you will. You can see on this diagram, right where we're talking here, let me get the right color. You're going to have still your main pressure valve. That's going to be what really controls the majority of your pressure. However, you also want to have recirc and concentrate needle valves, so you can influence how much fluid is flowing in either direction. Okay, and the recirc needle valve, if you tighten it down a little bit, it will restrict that, and obviously it'll make more fluid come out through your output, your concentrate output. And conversely, if you were to tighten this one down a little bit more than this one, it will force it to go more through the recirc line. Okay, so you can have a range from 0 recirc up to, let's say, 100, but 100 would be crazy because you'd have kind of an infinite loop that wouldn't work, and we can talk about why. But let's assume maybe upwards of like 75% of your recirculation. And I want to go through kind of an analysis that shows you 0%, 25%, 50%, and 75% of the output coming through this pressure needle valve being split off into the recirc loop. And that recirc loop is coming back in right here, mixing in with your raw sap. So the sugar concentration of what's coming into your system is slightly increasing. And eventually the output reaches a level that no matter, it can't go any higher for various reasons, because that max coming out, mixing back in with raw sap, still results in the same max coming back out. It's an asymptotic relationship, and we'll show you that on a graph. But again, that recirc's going this way, your final concentrate's going this way, and you want to be able to control that split and influence your final output rate as well as your final output sugar percentage. The more you recirc, the higher your sugar percentage is going to get coming out of your output, but the lower your flow rate will be. Okay, and I'll show you that on a chart in a second here. Okay, so I want to walk through an example of various range of recirc rates and the influence on the final output flow rate as well as the max sugar output, and so your concentration factor is also changing. For the purposes of this example, we're kind of going to make some simplified assumptions just to make this easy. This is set up right now for a 6 membrane by 600 gallon per day, and our 600 gallon per day membranes, we're assuming, are rejecting a fixed 6 gallons of permeate per hour. There's a lot of reasons why we're assuming that. Number one, that's about what you see in real life. They tend to be rated to about 25% of the full rating because of the sugar concentration as well as the temperature of the sap. Now, that's assuming at a certain net driving pressure and a certain recovery rate that you're going to get that fixed rate and a certain osmotic pressure. Osmotic pressure is the pressure required to separate the water from the solution. As that solution concentration increases, osmotic pressure increases. So if you get a sugar concentration very high, you need a very high net driving pressure to be able to separate that water out through the membrane. For the purposes of talking through this, we're going to assume, and this is justifiable, by the way, in all the math, that our pump pressure and the flow rates and everything work fine. Our osmotic pressure is not going to get too high because we're going to keep everything below 7%, and we're going to be around 120 psi, 115, 120 psi. And our flow rates and recovery rates are all going to be fine. So we've got a spreadsheet here for each scenario. At 0%, we're just starting with 1.5% sugar concentration and then the time step. And you're feeding back none of the recirc. So you're rejecting out the 6 times 6, 36 gallons of permeate per hour, and you can see what your final sugar output is, which is 2.85%, which is going to just stay steady. Okay, so you're putting that out at 40 gallons per hour, not quite doubling your concentration, and that's with 0% recirc. And then 25%, we do the same thing. We run through it, and for each step increment you're taking and adding this percentage of sugar at some recirc rate, so some percent of that flow rate coming back and mixing with raw sap. So this feed sugar is going to slowly increase, and so is your output sugar. And again, you're rejecting a fixed amount of permeate per time step through this analysis, and that results in 30 gallons per hour output with a concentration of 2.2, and your max sugar is 3.3 coming out. Okay, and your max sugar going in, that mixed stream of recirc plus raw sap, is now 1.74. Okay, so this gives you a little bit higher concentration and a little lower output flow rate yet. And then 50% scenario cuts you down to 20, which makes sense, right? So half of our original output of 40 is now coming out, which is 20. Your concentration factor is 2.8. Your max sugar percentage is 4.2. And you'll see also your feed is increasing slightly because you're mixing a higher percent sugar concentration back in to your raw sap. Okay, so now 75%, this gets more interesting, right? We go all the way down to just 10 gallons per hour coming out, and our concentration factor is all the way up to 4.6. So we've got a max sugar concentration of 6.9. Okay, this is about as high as you really want to go. You could potentially go a little bit higher, but the efficiency and usefulness of your membranes is going to decrease, especially that last membrane in the array. That's going to start to degrade from a performance standpoint. You may not realize the full 6-gallon flux of permeate out of it. Okay. All right, so let's look at the summary data. So for each test case, you can see the summary here, ranging from 0% recirculation. So your recirc line ball valve is completely closed here. You're going to get a sugar concentration output of 2.85% coming from 1.5. Again, we're just using 1.5 in this test case. Your sugar concentration may be higher or lower than that. So you're going to not quite double the concentration. You're going to get 40-gallon outflow. 25%. This is where 25% of the total throughput in your system is coming back through your recirc loop, and 75% is going out your concentration line. Okay, so you've got the needle valve on your output side a little more open, and your needle valve on your concentrate recirc a little more closed down. So you're getting, again, about 25% back through. 50% is an even split, so they're both open the same amount or backed all the way out. And 75% over here is, again, kind of the reverse of 25. You're going to have more going through your recirc loop and a little bit less coming out through your final output loop. And you're going to get only 10 gallons, but you're going all the way up to the 7%. So one thing to think about here, again, is you're going to have pretty much a fixed amount of permeate coming out. This is just changing how much concentrate is coming out and what percent sugar it is, right? So it's speeding it up in some ways, but the key is to try to match this output to your boiling rate, okay? For example, if your evaporator can handle 30 gallons per hour, well, I would start with this configuration and just be feeding it in near real time. So that way you're not waiting on your RO, or your evaporator isn't, or you're not waiting for your evaporator, right? And you've got a bunch of concentrate built up and you're waiting to boil it. Though some of you might want to run your RO in advance and have it ready to go, then why not go all the way to the recirc, right? To the higher level of recirc and get that concentration up as high as possible. Let the RO do most of the work in removing water. They're much more efficient and cost effective than boiling. Okay, so here's the asymptotic behavior that we talked about, right? We showed you that time series set of tabs, and you can see the 2.8% is just flat straight across with no recirc, and then the 25%, the 50%, and the 75%, and they all increase and level off. Now, this is we said like minutes in the spreadsheet. Don't think of it as actual minutes. I just did time steps just so you could calculate and do the mass balance of feeding the recirc back into the raw sap line and all that. But just as a step of time, and over time it'll asymptotically. This actually happens pretty quick in reality. Okay, this gets up to your max value and levels off and holds steady. Okay, so I hope this explanation helps clarify how recirculation works, why it works. I've also been asked some questions about how do you measure the output of all this? Okay, well, the answer to that is kind of two different ways. Number one, flow meters, right? You can buy flow meters to monitor your concentrate rate of flow, your recirc rate of flow, and your permeate rates of flow. But you can also use containers that are of a known size and a stopwatch. So a 5-gallon bucket, how long does it take to fill that up? And you can calculate your gallons per minute or gallons per hour or liters per minute or liters per hour based upon that. So all of this stuff I've done. I've got actually some pretty complicated spreadsheets and a Python program that helped me design a lot of the systems. It's done on paper, but then we bench test the pumps at different pressures to validate the flow, the pump curve, the performance curve, what flow rate at what pressures. I've tested a lot of these different configurations, measured the outputs over the years. So this is all pretty realistic data based upon analysis as well as test results. So anyhow, hope this all helps, guys, and answers a lot of the questions that you all have had in the past. Appreciate it. If you like this video, please be sure to like it and also check out all of our other content on our channel, and please subscribe. Thanks again.